Swayam Prabha. Digital India. Educated India.
Okay, yeah. So yesterday we have discussed about this fluidized bed and bubbles in fluidized bed. Now I gave you this. Okay, you take in this the first figure. Can you see the first figure? Give them. Yeah, please see the first figure. What do you see? First figure is small figure put on side. Yeah, did I draw this figure on the board? Yeah, I have drawn this figure yesterday on the board, but he has drawn the actual lines later, which will also predict those points. Okay. So, this is more informative than yesterday what I have given, because yesterday I want to pose the problem, but in this solution also is given. You can see the topmost line and top two lines in fact. What are the top two lines? For small dp. Small dp means what kind of bubbles we get? Very small bubbles, delta b, delta A particles, okay. Small bubbles and more number of bubbles. So, they move much faster, okay. And so, if you analyze this in terms of large diameter and small diameter of the particles, which will automatically take care of your bubble size, then you can also predict whatever we have discussed yesterday. Okay. So, that is figure 1. Figure 1 I think you know what we have done, and as I told you, you see there he has written also 39 experimental studies. So, without bubbling model we do not know how to predict that, because they are all over the graph. Okay. So, now with bubbling bed model, that means when you take the bubbles into account, then we can try to predict. That is what we have to derive now, the bubbling bed model, right. So, for that that is the first figure. And what is second figure? Second figure is just a picture of how the fluidized bed looks like, with bubbles. Okay. You can see a lot of information is there on that. If you see that that row of bubbles just going up, you have small bubble, while it is moving up it goes it grows, and when it is growing its wake also is increasing. That means it is taking more and more particles along with it to the top, and once it goes and then breaks there, you see there is a thick arrow. Those are the solids. US is given there, if you look very carefully. US is the solid velocity which is coming down, right. So, the general assumption in fluidized bed is that there is a continuous movement of solids in the fluidized bed, where particles are taken by the wakes, by the bubbles in the wakes, and then they go leave the bubbles, leave the solids there, because something is going from the bottom to fill up that gap, something else has to come. Okay. So, that is why recirculations for solids, and then you will have good mixing because of the bubbles, right. And if you do not have good mixing, the beautiful property of same temperature, same concentration will not be there for fluidized bed. So, that is the reason why that is the basics. Again, we are talking about basics whenever we talk about these things. Our basic thing, mixed flow reactor is we should have same temperature, same concentration in a mixed flow reactor, which is equivalent to our plug flow reactor, sorry, our fluidized bed reactor. So, that is that figure. And figure 3, if you see, that is the actually, if you take one bubble, what is really happening in that one bubble, and before understanding that bubble, okay, that figure 3, you can come to figure 4. This is what yesterday I have explained to you. Figure 4, the first one is in that out of there are 6 figures, the top row, first figure, you have UBR equal to 0. What is the meaning? They are stationary bubbles, they are not moving, just going there, and the gas in the emulsion at minimum fluidization velocity is simply going through the bed. Bubble is stationary there, right. So, as I told you yesterday, this gas will use this bubble as a short circuit and then it will try to go through that. See that these are the streamlines which are going through that, these are the gas streamlines, the arrows which are going through that, right. And now you see, if the bubble started moving, not UBR equal to not UBR equal to 0 first one, UBR not equal to 0 second one, in fact UBR by UF equal to 0.6. You see now how the streamlines are taking turns, and one of the streamlines at the edge of the bubble is already circulated. Okay. So, now you see when UBR equal to UF, the next figure, that is UBR equal to 1, UBR by UF equal to 1, there the gas already started recirculating, but still there are no clouds, right. Even at UBR equal to UF, still there is no cloud there. You could observe, no, that you will observe in the next figure. When UBR equal to 1.1 UF, just 1.1 UF, you can see the cloud forming. Okay. You can see the cloud forming, and Davidson has also derived an equation for calculating cloud radius, RC by RB whole cubed equal to, you have UBR and UF, those two velocities. UF is UMF by epsilon MF, okay, that yesterday I have written there. So, that is how the cloud comes, and when the bubble velocity is increasing, now you see in the next figure UBR is 7 times UF. If UBR is 1 centimeter per second, UF when UF is 1 centimeter per second, UBR is 7 centimeters per second, that means bubble is going much faster. So, it will make more of the gas circulating within the bubble, and also cloud also reduces, and you see UBR by UF greater than 100, cloud thickness is almost 0. So, that means most of the gas now started recirculating, please carefully observe, within the bubble itself. So, when most of the gas is started recirculating within the bubble, where is the possibility for the bubble, for the gas to come out and then react with the solid? That is the reason why you have gone to that worst, even above mixed flow, because absolutely no contact between the solids and then gas, all the gas is going within the bubbles, and particularly when you have the flow rate through the bed is maybe 100 times UMF, 50 times UMF, 60 times UMF, minimum flotation velocity, actual bubble velocity is 50 times to 100 times UMF, then the bubbles will go much faster, then you will have very thin clouds, but most of the gas is circulating within the bubbles itself. So, absolutely there is no contact between the solids and the gas. So, that is the reason why there is no reaction at all. Yeah, I think.
Which circulation of gas happens?
Yeah, that is true, that is happening, but when you go to the last figure, cloud disappeared. So, most of the gas is only circulating within the bubble, that is worst scenario.
So, in reality, how do you how can you see the boundaries of the bubble and the cloud separately? I mean, what is there in the cloud exactly?
Cloud is gas, not cloud, bubble is gas, cloud is particles. But
Particles in the cloud different from the particles outside?
They are slightly different, because the bubble is just moving. When it is just moving, the particles are there just on the roof, right. So, whatever particles which are not falling through down, okay, and when it is just pushing, those particles, if you see the local void edge, that will be slightly smaller than the outside. Okay, that is only the difference, and you can see that one, because you asked a very good question. See the next figure, next slide, figure 5, that is the actual bubble that is taken by photograph. You see all other places slightly, you have that dark area, right, and then around that you have more dense particles, and away from that is slightly less dense particles. And another beautiful thing what you can see is, the wake, how the solids are going with the wake. See, Davidson theory was beautifully measured also with experiments, and you can see the next one. Next one means B, 5B. Those are the streamlines, in fact. Okay. So, this is in fact this is one of the greatest I think I say discoveries in chemical engineering with respect to fluid aged beds. Really beautiful that theory, Davidson. Okay. And of course, Harrison, Davidson and Harrison, these are the two people. I think I have to just write that also. These are the two people from Cambridge University who have done this, but the first person is Davidson alone has done lot of work on the bubbles. Okay. Yeah, if my remembrance is correct, I think Davidson was mechanical engineer, I think, but he liked so many chemical engineering problems, he shifted to chemical engineering and first started doing work on gas liquid systems. I think he was working in ICI, if I remember correctly, and then he developed some bubble columns for ICI at that time. I am talking about 50s, 40s and 50s, and this theory is mostly by 62, 67 we have thorough theory for even gas solid system bubbles. He knows liquid gas system. Okay, that is normal. We know, all of us know how the bubbles go in the liquid. Okay, that is everyday phenomena for us. When you are taking any drink, okay, so you can see how the bubbles come up, and when you see any aquarium, you can see a lot of bubbles coming up. So all that, but we never get excited, when the bubbles are coming, because I think maybe we will look at only fish. When can I eat that fish? Okay, and we are losing the beautiful part of the bubbles, which is very important for us. Okay, so that is the reason maybe we never bother. But I think he has done a lot of work, and then afterwards he extended the same theory with some assumptions for the bubbles in solids, and many people did not believe, even though many people do not believe that there are bubbles in the fluid aged bed. But if you come to our lab, I can show you. Okay, yeah, I think ask Gunjan when he has removed the packing, and then he can show beautifully the bubbles how they are coming, and some of the bubbles will crawl near the surface where you can see, right. And this photograph was done with the two-dimensional column. Two-dimensional column means they take just two plates like this, okay, and then bottom there is a distributor plate. They inject one bubble. When that bubble is moving slowly, then of course they can control that movement with slow injection, and then that is taken, this photograph is taken when this bubble was slowly moving, right. I mean, it is beautiful, no. I think some time back this PhD students used to conduct quiz. I only pushed them when I was HOD, I think. Yeah. So they used to 3 years they conducted this quiz for chemical engineering students, including BTechs they used to come, but PhD students I asked them to take the lead. Okay. So in fact I gave this one, different faculty members gave different questions. I gave this as photograph and asked the students to identify what is it. Okay, only without writing anything, just this photograph, and then showing. I think just 1 or 2 people say atomic bomb. Okay, correct? No, same thing. Yeah, it is really atomic bomb as far as fluidization is concerned, because if we do not understand this, we do not know anything how to characterize fluidization at all. Okay, good. So this is the one, and now yeah, you see the this side all the figures we have explained, right. Yeah, and if you see now figure 3, please go to the other side. Figure 3, now when I told after figure we will come back. So there it will give you more clear picture about how the solids are moving even in the clouds, or how the solids are moving slightly away from clouds, and how the recirculation of gas is taking place. At least physics you please remember, I say physics please remember, the inefficiency of the fluid aged bed is due to the bubbles, where fast moving bubbles will not allow gas to come out of the bubbles, so that there will not be any contact between the solids and this gas. So then where is the reaction? The other part of the bed, the amount of gas going is very, very small. I told you, if normally in the industrial reactors you use 20 times, 30 times, 40 times UMF, but how much gas is going through the emulsion, the other part of the bed? Only one UMF, right. So that is the reason why very small amount of gas is going through the solids, and you will not have much reaction, because there should be more concentration. See, the rate of reaction depends on concentration of gas, amount of gas. Okay. So when most of the gas is going in the form of bubbles, very small amount of gas is going through the solids, that is emulsion. Where is the reaction? you do not get that kind of high reactions. Okay. So, that is the inefficiency in the fluidized bed, and that is why people try to do that. I told shallow beds can be used, for example. That means where there is no time for the gas bubble to form, grow and then move up, right. So, shallow beds means if the diameter is 1 meter, you take only half meter height, okay, half meter height solids. So, then you will not have this kind of big problem. You will have still small bubbles coming and going very quickly out, but I think they will not destroy the bed so much. Some people started shaking the bed, because by shaking the bed you may also have bubbles, bubbles not forming at the distributor plate itself. I told how this bubbles may be forming is, you have one perforation, the gas will try to go into that, it is not able to go because a lot of solids are there, then it slowly started pushing the solids. Like when you want to go through the crowd, what do? You push all the people there a little bit forward. Okay. So, that means you are creating a void when you are pushing them for you to move. So, that is what gas also is trying to do. When it is trying to do, then at one time it will form sufficient volume, where by buoyancy it will detach from the perforation. From then onwards it grows. So, by shaking your perforated plate or the entire column, what is happening? You are not allowing that kind of pushing the solids, pushing the gas, pushing the gas pushing the solids, it is not happening. Okay. So, that is what some people did, and some people did that, okay, we will take the large height of the beds, but put distributor plates in between, for example sieves. Okay. So, idea is bubble at the bottom will grow and then come and hits the sieve in between. So, it may break and again another bubbles may form, but at least that bubble is destroyed. So, all these techniques also have been done to improve the performance of fluidized beds. Okay. So, that is the one. So, if you go to the next page, figure 6 is same thing what we have done earlier also. That means how slow bubbles, the gas is bypassing through the bubbles for slow bubbles, that is the right hand side of figure 6, and left hand side what you have is bubbles going faster. So, circulations are within the bubble and within the cloud. Okay, good. So, then figure 7 now is the picture for the bubbling bed model. In fact, Davidson and Harrison, what they have done was that they thought that bubbles and solids they have separated, like our two phase region. The other day I have drawn that two phase region model. Okay, that model they have followed, right. So, with knowing clearly how much is there in the clouds and wakes and all that, but they consider clouds, wakes, everything in the solids, only bubbles are moving. Then they have also proposed a model which was not very good in the prediction wise, but they never accept that. In fact, Cambridge University people never accept Levenspiel model. Okay. There are two groups in the world, one is that Cambridge group, another one is this Kunii Levenspiel group. Okay. Kunii Levenspiel Kunii Levenspiel model. This is Davidson Harrison model, that is two phase model, and this one two region model, and this Kunii Levenspiel model is three phase model or three region model, where they have taken separately bubble phase and they have taken wakes and clouds, where definitely there is more contact, right. When compared to the emulsion, in this region there is more contact of gas with the solids, because they are moving with the entire gas. Okay. So, that is another region, and from there it goes to emulsion. Now, if you imagine the first thing what I have told you in the beginning, how do you develop this rate of reaction for heterogeneous systems? Okay. You write all the steps together, right. Now, here step 1 is the bubble gas. If there are solids, there is some reaction in the bubble, then transfer of this gas to the clouds and wakes, because those are the nearest ones. Okay. So, then this transfer, that is mass transfer to the clouds and wakes. Now, because there are solid particles, reaction conditions, now there is reaction in clouds and wakes. Now, whatever gas is left further, it will be transported to emulsion, and from there it cannot go anywhere. it has to react under steady state conditions. You see, no, but here beauty here is this is parallel steps and also series steps. Series and parallel steps both are coming here. What are the series steps? Series steps are mass transfer steps from bubble to mass going to the clouds and wake, from clouds and wakes to emulsion. Parallel steps is in all these things the reaction going on in bubbles, reaction going on in clouds and wakes, reaction going on in emulsion. So, that is the overall concept of this entire bubbling bed model. So, then it is only mathematical details. Okay? And you have to really excuse me here in the sense that I am going to write some parameters for writing this, for finally writing bubbling bed model, but some of the parameters actually takes 1 or 2 chapters in those books for the derivation. Okay? But we have to blindly accept that, right, thinking that, but they are now very well established. I am not cheating you, but they are very well established, but definitely I also agree with you that if you have a physical feeling that for that equation the pleasure is different. Okay? That is what I say, really when you enjoy, you enjoy only when you have the physical feel for the problem what you are doing. And some of the classes you may enjoy because you think that you have understood, you are also part of that the phenomena, then only you start enjoying that. But for that much effort is required from your side, it is not only from teacher's side. Okay? I mean teachers also can kill your enthusiasm. If everything is confusing to you, then definitely you will never, you will try to understand in first 1 2 weeks, and if you are not able to follow anything, switch off. What switch off? Brain. Okay? Till now it will be open, the moment you enter the room, classroom, switch off, you will be laughing, you will be enjoying and all that, that is different, but still it is locked. Okay? So, when after class is over, go and again switch on the brain. So, nothing will go. I mean exactly it is two way, reversible reaction. If a teacher is lousy also can kill you, if you are yourself is not interested in learning, then that also can kill you. Okay? So, that is why I mean all my teaching always is always to try to bring at least one more person for interesting side, that is all, one more in every class, one more. Okay? I do not have 40 people now here, we have taken 40 classes. Okay. So, that is the model, but let us now take, yeah, I am sure you might just now temporarily Abhinav, anything?
Assumes that the concentration of the gas inside the cloud is also uniform. They don't, there is no mass transfer.
No, not in the direction where it is going. Okay, what they have taken is they have taken one slice in the bed at any one cross section, and then you write the balance here. That balance is I have a one bubble, the bed height is so much. In between you take a thin slice, because along the height of the bed we have to integrate anyway. Okay, yeah. So, dz you take and then write the balance for this, that is if there is one bubble there in that slice. So, the reaction is going on in the bubble if there are solids. People found that there are very small number of solids, sometimes you can neglect, sometimes you can also add, it is not going to change the value that much, okay? But normally we will add to see. So, reaction then transfer to the clouds and wake in the same level, horizontal direction. Why it has to go? Because concentration gradient is, there is concentration gradient.
According to this, there is only
which figure you are referring to?
Figure 9. So, there is a different concentration in the emulsion and a different concentration in the cloud, but there is no concentration difference within the cloud.
Within the cloud we do not expect, sorry, within the cloud, yeah, CIC, no, it is not. Assumption is that you have uniform concentration throughout the cloud, right? Not only cloud, even in the wakes and cloud, yeah. And emulsion there is only one concentration, and in the bubbles there is another concentration which is CAB.
So, because I asked you this question because if the figure 4 shows the slow bubble moving and the cloud radius is comparable to the bubble radius. And
that is slow bubbles. No, which figure you are referring? In figure 4.
So, in that case, would it be a valid assumption that the concentration inside the cloud would be equal?
Yeah, see, the validity automatically comes when you have the experimental data being verified, that right. Even then this is not perfect model, I tell you, there are still many assumptions in this. When you derive the actual the equations which I am going to derive, you will have hell. I mean, what is that finally we are trying to do? There are many assumptions, but with all those assumptions, figure 1, if you see, I think figure 1, the side figure, there is a side small figure, side, yeah, that one. You see that line, the first line, that is predicting for the small diameter particles. You see what is, how much scattering is there around that line. Those are the actual experimental data. Okay? So, that is why there are assumptions. You may feel that yes, there may not be uniform concentration throughout the cloud. Okay? So, but you can't do better than this. That is why this model is accepted, and any delta x improvements you can always do with more and more mathematics. Okay? Any other questions? Yeah, and the figure 10 where the equation is there, that will only, I think Levenspiel has used some other same thing only, but the basis has been changed. So, this equation we are not going to derive. I think other equation we are going to derive, that equation which you have to use if it is given in the examination. Okay? That is the equation. So, this equation is from his old book, and in the recent 3rd edition where you have the book, 3rd edition Levenspiel. So, I can't use this equation because I think if you want to go through the book, I have to draw, I better draw that particular equations. Okay? So, that is the reason why, except that all the other figures are valid for our discussion. Okay? But you will get very similar one, but only thing is that material balance is not proper, because here he has used the balance based on volume of the bubbles all the time. I told rate of reaction can be expressed in various ways for heterogeneous systems. Weight of the solids, volume of the bed, volume of the bubbles, that is void edge. So, all that, but here it is volume of the bubbles, but in the book he has used volume of the bed. That is why there is an extra factor coming delta. Delta is the fraction of bubbles per unit volume of the bed. So, that is the way that equation will be slightly different, format exactly same thing, same format you have, same, but terms will be slightly different. Good. Okay. So, now I am sure you think that you have understood, but oh my god, yeah, you may not remember after some time, right. So, that is why let me give some notes, at least for those people I think who want to read again before the examination and all that, at least this will be there. You are not lost totally, unless otherwise you read the fluidization book or Levenspiel CRE book edition 3, where he has beautifully summarized also, right. So, it does not mean that do not take this and only go and read that. Okay. So, but please write, once more writing nothing will harm you, your health will be perfectly okay by writing this thing what I am going to tell you, but still if you read it is fine. So, hydrodynamic model, okay. The discouraging results, you can just write below that. The discouraging results with the previous approaches. What are the previous approaches? You can write if you want, yeah, 1 parameter model, RTD model, CTD model, 2 region model, that is in the bracket. Okay. Let us reluctantly to the conclusion that we must know more about what goes in the bed, if we develop a reasonable predictive flow model. To develop a reasonable predictive flow model, that is hydrodynamic flow model. Okay? Hydrodynamic flow model. In particular, we must learn more about the behavior of rising bubbles, rising gas bubbles, since they probably cause much of the difficulty. Next para you can write, 2 developments are important in this regard. The first one is Davidson's remarkable theoretical development and experimental verification. Of the flow of gas in the vicinity of a single rising bubble in a fluidized bed. okay, in a fluidized bed. So, yeah, from where of the flow in the vicinity of a single rising bubble or before that. Okay, I will read from the beginning. The first is Davidson's remarkable theoretical development and experimental verification of the flow of gas, in the vicinity of a single rising bubble in fluidized bed, which is otherwise at UMF. That means the fluidized bed is at UMF, okay? Only bubble is rising, which is otherwise at UMF. Okay? Yeah. He found that for fast rising bubbles, yeah, the gas recirculates within or the gas recirculates within the bubble, within and cloud, recirculates within the bubble and the cloud. Yeah, that means here important thing what you have to note down is that bubbles have clouds and the gas is trying to recirculate within the cloud and then also within the bubble, but under extreme conditions all the gas only may circulate within the bubbles. So, that will be worst condition where to get very very low performance in fluidized bed. Okay? That is the one. So, I think there are many things, but still I think I will just cut down that one. The second finding, first one was that the model development for the bubble itself. Second one is the second finding on single bubbles is that every rising gas bubble drags behind. The second finding on single bubbles is that every rising bubble, gas bubble, drags behind it a wake of solids defined as alpha equal to volume of wake divided by volume of bubble. Oh my God. Yeah, alpha, okay, that you can write. Yeah. Alpha varies, stop there, alpha varies between 0.2 to alpha varies between 0.2 to 0.222. Okay, 1 2 is TO, another T is TWO. Okay, 0.2 to 0.222. Okay, yeah. So, this is one, and Levenspiel very beautifully says that depending on, please continue, 0.222 depending on who reports the results. Really, it is so vague. Really, here I think Abhinav was asking, yeah, all these perfect things are there, but I think measurement also is very difficult to find out. That means just imagine alpha is volume of wake by volume of the bubble, no, right. So, what is the meaning of 2? If alpha is 2, what is the meaning? Huh? So, I mean, how can it be? That means, you have a small person trying to carry 2 tons to 3 tons on his head, or just hanging, try to lift, which is very difficult, no? So many solids to be lifted up. Yeah, volume, that is related, no? If you have the I mean, what do you contain in that volume? Yeah, that is what, but those are solids only, right, nothing else in the wake. So, solids have some density, whatever density that we can see, but definitely the volume sizes also indicate indirectly the weight also, no. So, that is just to tell this, that it is not that easy to measure the wake volumes and all that. That is why you can't expect perfect matching of experimental results with the theory. Okay. So, in fact, in all multi-phase systems this is the problem. That is why I like chemical engineering, because there are so many things. Even now for you, if you are really interested in fluidized beds, I can tell you 110 problems in gas solid fluidized beds, not 1 or 2, even now. Okay. So, every question what you ask, every doubt what you ask is a research problem. Like he was telling, no sir, how can it be true that there is a concentration same throughout the cloud? That is a research problem for us. You can actually send a single bubble and change various velocities and try to measure those concentrations in the entire cloud from bottom to the top around the bubble. okay, like this one, this is very vague 0.222. So, what is the exact amount can you measure, because as technology is increasing, then sophistication in measurement also increases. So, we will have now excellent measurement techniques. So, without disturbing any bed at all, you can try to measure from outside, no in situ measurements, only from outside. Okay. So, that is called non destructive testing and all that. So, just watch from outside and then you can get maximum information by using some kind of gadgets, like finally it goes to like science fiction movies, right. Yeah, like this, all the planets also may move. Yeah, that is the kind of movies they show, no, that like this. I think now recently I started seeing one Axe advertisement. Axe advertisements are all crazy advertisements, So, one boy will be he will say that. So, from I think the latest one is from some planet also she pushes like this, she says like this, then her rocket will come to India, so finally she comes to his room. Okay, so that kind of science fiction, from smelling, diffusion, how fast the diffusion must be. This fellow, this fellow is not even completely sprayed. She starts there, then she smells that there in some other planet. My God, it is instantaneous diffusion throughout the universe. That is fantastic. Even light cannot travel so fast, but Axe smell can travel. So wonderful, no? His imagination, very good. Okay, good. So this is another one. These two are the important findings, because for us there are clouds, wake, where there is some amount of solids. Now I think cached on this information, Kunii Levenspiel developed their own model. Before that, Davidson developed another model using only bubbles and all the solids, like exactly two region model what we have discussed earlier. Okay, but they have not used so many parameters, like 6 parameters they have not used, but they simplified the parameters, and it was to some extent for some reactions it was able to predict. Then came Kunii and Levenspiel. Kunii is from Japan and Levenspiel is from USA. Both of them met, it seems, in one of the chemical engineering conferences, because I think their story also is very nice, because both of them travelling from Chicago to somewhere or so by train. So, I think Kunii son or daughter, small child, I think went and scratched Levenspiel, because in the train when they are moving that is the starting point. I think she was the catalyst. So, then they become friend, normally that happens. For us also, when you are travelling, what is the center of attraction generally if you want to make friendship with someone? Children. Okay, you will go and say hey, like that. then mother and father automatically will become friends to you. So, it is exactly same thing happened for Levenspiel and Kunii. I read this a long time back in one of the articles. Okay. From then onwards their collaboration is fantastic, and that book Kunii Levenspiel is one of the excellent books for fluidization, and the title is Fluidization Engineering. I do not know whether you heard of that or not. Davidson Harrison also wrote this big book, but Satyajit Ray movie. Okay. Because because they only tell the facts, truth, always huts and all that, no poverty. Other who will read that book? Okay, who will go to Satyajit Ray? How many of you seen Satyajit Ray movies? Okay, not even one. No, Kavya, you are interested? Satyajit Ray movies. Oh, good. Then for you should read Davidson Harrison book. But whereas Kunii Levenspiel book with beautiful examples, nice presentation, I can tell you Kunii is a lousy writer. The papers written by Kunii alone, if you want to read, you can never read even abstract. Okay, abstract may be 10 lines or maximum 5 lines. Okay, of the papers I am telling you cannot, but it is Levenspiel who changed him also for presentation. Wonderful presentation again. Kunii Levenspiel book library also it must be there. You can just go and see what beautiful way the bubbles he represents and all that. Of course, you can see that in third edition of Levenspiel also, where he has just copied from there to this book. Levenspiel clarity is fantastic. I think in my opinion he is the truest engineer. But many people in the US it seems he won't like chemical engineers, because he will try to simplify things. Okay, he won't use complications, right? So that is why. And if you read his papers also, his research papers, almost many papers I can tell you 60 to 70% of the papers will have worked out examples in the papers. Research papers normally no one gives worked out example, and all this information what we are going to discuss for Kunii Levenspiel model also came in 6 to 7 papers. in every paper. Okay. There is one, at least one worked out example where that gives you the clarity. The moment you try to put numerical values, calculate and then get the feeling, you will automatically get the feeling. So, that is the kind of, I think Levenspiel is great, who made CRE very simple. Before that there were two books, Wallace book, reaction or that kinetics for chemical engineers or so, and before that Augen Watson, these two books. I think no one I think read also that, maybe Wallace is slightly better, but when Levenspiel book came only, it went to throughout the world as chemical reaction engineering subject after you wrote that book. All of you got this? Okay. Oh yeah. I will also give you, you can distribute them, let them, you have this with you. I thought I will give in the next class, but I think, but do not throw them out. These are the problems in fluidized bed reactors and also slurry reactors, this advanced booking. Okay, because I have not done both now, right? Fluidized bed we are doing, but slurry reactor there are just one or two problems. You can do that as far as possible. Whatever I know, answers also I have given, but then just keep it with you and then solve.